Hello, students of science. In this video, we're going to talk about the reaction process and a little bit over collision theory, activation energy, and potential energy diagrams. Let's get started. Chemical reactions do not usually occur in a single simple step. I know that we've been really showing those equations with a very simple starts with this, goes to this. It doesn't really go that way. Most reactions are actually pretty complex. There's a lot of in-between steps, and you have the appearance of chemical species that don't actually appear in the overall balanced equation. We call these in-between little things intermediates. Let's say we have phenol plus something else is going to react and make salicylic acid. It's not quite that simple. There's a whole bunch of other reaction mechanisms that we're not actually showing. All those different things, those are intermediates. Those don't actually appear in the chemical equation. The carbon dioxide will, but that's about it. The simplified equation doesn't even show the reaction mechanism. It doesn't show those step-by-step sequence of reactions for how that change occurs, where the electrons move here, and then the bromine goes here, and then hydroxide. All those things don't necessarily show up in our equation, but that doesn't mean they don't actually happen. You can even have an incredibly complicated reaction, like this particular one right here. I have these different things attacking different parts in there. Electrons are jumping from one to the other. You have all these different things. That does not show up in your equation. All you really have is the beginning and the end. Also, any reaction that occurs between chemical species in the same phase, be it liquid or gas, like two liquids reacting together or two gases, we would call that a homogeneous reaction because they're in the same phase. So this would be a homogeneous reaction, a single liquid phase. There might be a couple of things in there, but it's all liquids, as opposed to something right here called a heterogeneous reaction. We have something solid dissolved in something liquid, or something liquid in a gas, that sort of thing. Reactions can also occur at very different rates. Some reactions are nearly instantaneous, others can be literally years long. That's how long it would take for them to react under suboptimal conditions. In general, however, one kind of rule of thumb, the fewer the number of intermediate steps, all those little things jumping around, the faster the reaction is going to take place. So normally we have just like a single activation energy. In this case right here, we have almost two of them, two transition states where it goes from one, then it transitions, and then it transitions again to the other. And in between, we have our intermediates, the things that don't appear in the final form. Here we have one that has two intermediates. So in general, the fewer intermediates we have, here we have only one, the faster the reaction is actually going to occur. So this one would be faster in theory than this one here, based on the fact that this one has multiple steps in the middle. Collision theory is how we actually determine whether or not two chemicals are going to react. So there's a couple basic ideas to it. First off, molecules have to collide. You can't have the breaking of the bonds and the exchanging of the electrons unless they're actually touching each other. Here we have an unsuccessful collision, and here we have a successful collision. For a successful collision, the molecules have to also be correctly oriented. So here we have some molecules bouncing around, and those first two collisions, even those ones, they connected, they hit, but that wasn't correctly oriented, so there won't actually be a reaction. Only that last one there was a properly oriented chemical reaction. Molecules also have to be moving fast enough for them to react. By this, we mean they have to have a lot of kinetic energy, and the kinetic energy, that is essentially the temperature. Temperature is the average kinetic energy of the particles inside the substance. You need that kinetic energy because you're going to be breaking bonds and new ones are going to be formed. Electrons are going to be transferred and atoms are going to organize. If you don't have enough kinetic energy, the reaction is not going to happen. When we've been talking about the enthalpy of formation, this is really what we're saying. You have to have a bare minimum amount of kinetic energy to actually form this particular compound. Otherwise, you can't break those bonds, you can't make the new ones, and you can't transfer and organize the electrons and the atoms. Activation energy is really what we need to get over. Activation energy is the energy needed to start a reaction. You don't have it, you're not going over it. Think of it as like a guy pushing a boulder. He's got to get it from A to B. He needs to get it down there. However, there's that hill in the way. That hill is the activation energy, or E sub A. A high activation energy requires a lot of energy to get the reaction started. Even if that reaction is highly exothermic, even if there's a very, very large negative delta H, there could be a cliff on the other side of the hill. It doesn't matter. You still need to get it up and over that hill. The higher it is, the harder it's going to be, no matter what's on the other side. Low activation energies are usually going to proceed quickly, maybe like a little small hill going down. But a high activation energy, those reactions are going to happen slowly, or they're only going to happen at a very, very high temperature. A lot of kinetic energy, a lot of heat to push that rock over. So an activated complex is a temporary transitional structure that you'll only find while the old bonds are breaking and the new bonds are being formed. So on our potential energy diagram, so this is my activation energy, the energy I need to get up and over there. Only at the very top do we see that activated complex, that temporary structure. You only see this with an effective collision, when there's enough kinetic energy and correct orientation. So here's my reactants, there's the product. Activated complex is the maximum amount of energy we get before it can start transitioning to the products. Anytime you're looking at a reaction pathway diagram, this is going to be the peak. Here's another one right here. The activated complex and the transition state are all right there. Now we can go down in our exothermic reaction to our products. Reactions that have multiple intermediate steps are going to have multiple activated complexes. Here's my reactants, there's the products. Here I have multiple activated complexes. There's one right there, there's another one right there. So and I have one intermediate there right in the middle. So let's look at our potential energy diagram. If you don't have one of these already, I want to make sure that you're writing this one down. Here's just kind of a basic one. So here's the potential energy. The higher we are in the y-axis, the more potential energy we have. Here I have a reaction where sugar and oxygen are going to be oxidized. That's my glucose, is going to be oxidized to make my carbon dioxide and water. So my reactants have quite a bit of potential energy. The products don't. This forward path going to the right is going to be the oxidation of glucose. This pink line right here represents the activation energy for the forward reaction, what you need to get from here down to there. However, there is also a reverse path, that's photosynthesis, where you're going to take the carbon dioxide and water and you're going to use the energy of light to go backwards. Well, the activation energy for that reverse reaction, you can see significantly higher. To go back and up over that hill, you got to use all the energy that you'd normally need to overcome the activation energy plus whatever negative delta H you had. So the reverse reaction has a very, very high activation energy, which is why it doesn't happen. And that right there represents the delta H. In this particular case, the burning of glucose to make carbon dioxide and water, that is going to be a negative delta H. That is an exothermic process. So let's take a look at a couple other potential energy diagrams we have here. The one on the left, this is an endothermic reaction. This one is going to have a positive delta H. This one on the right, that's going to be exothermic, that's going to be a negative delta H. But my reactants, my products, and that's my activation energy right there. Remember, the difference between the reactants and the products is the change in enthalpy, or the delta H. This one's positive, this one is negative. Two more I have right here. Another exothermic reaction, small activation energy, very large change in enthalpy. A lot of heat is going to be given off in this reaction. Very negative one. Here's going to be another one. Again, my products are going to be the exact same. However, my reactants start with a lot less potential energy. So in order to get from these reactants to those products, I need a lot of activation energy in there. Again, this is going to be an exothermic reaction. However, the delta H is going to be negative, but not as much so as this one. Not as much heat will be released in the right one as in the left one.